now we will be talking about paramagnetic materials. So we discussed about materials which have the tendency to actually move away from the strong magnetic field, or they have the tendency to actually go towards the weaker magnetic field, or these materials have the tendency to repel away from the magnetic field. Okay, but there are certain materials which are called paramagnetic materials. And what does these paramagnetic materials do? These paramagnetic materials, when they are kept in a magnetic field, then they acquire weak magnetism. What do? They acquire weak magnetism. Okay, they acquire weak magnetism. Okay, means they are magnetized. It is not like they are not magnetized, but they are not completely magnetized. Okay, so they are magnetized, but they don't acquire complete magnetism. Okay, so such a magnetism is weak magnetism, or you can say fairly enough magnetism they acquire. Okay, they will be attracted, they get attracted towards the applied magnetic field. Okay, so such materials are paramagnetic materials. So if we will keep them in a magnetic field, definitely these materials will actually get attracted towards the magnetic field, and magnetic field lines will they will allow magnetic field lines to pass through them. Okay, so this is what the characteristics of this material, these types of materials. Now, as far as some examples of paramagnetic materials are concerned, you see, how do I remember? I will tell you a trick. Okay, yum. Okay, at the end, if um is coming, yum is coming, okay, then they are paramagnetic materials. Okay, so most of them are. Like I was discussing that most expensive metal is not diamagnetic, it is paramagnetic. Okay, platinum. Okay, this is how also you can remember platinum, platinum. Magnesium, calcium, okay, aluminium, chromium, lithium, magnesium, platinum, potassium. Okay, all these are which I named just now, these all are paramagnetic in nature. So they acquire weak magnetism, they acquire magnetism when they are kept in a magnetic field. Okay, now let us talk little bit about more properties like relative magnetic permeability of a paramagnetic material and magnetic susceptibility, because these are two very important quantities for determining that whether the material is a very good is it getting magnetized very nicely or not. Okay, so that is something which we have to look for, okay, in a material, because then we can decide that where should we use it. Okay, where the material should be used, what can be its applications. So mu r is greater than 1. Okay, mu r, relative magnetic permeability, it is greater than 1 for a paramagnetic material, means it is not too high, it is not too low. Okay, it is greater than 1. Then comes the magnetic susceptibility. Okay, magnetic susceptibility. So magnetic, because it is greater than 1, and we know that mu r is 1 plus chi m, so it is obvious that chi m for a paramagnetic material should be greater than 1. It has to be positive. Okay, most importantly, because we studied that the chi m for a diamagnetic material was negative, but in case of paramagnetic materials it is positive. Okay, so this is what is little bit about the paramagnetic materials. Now let us talk about why do materials they get magnetized. Okay, They are getting magnetized. These materials are getting magnetized. So the question comes that why do they get magnetized? Let us discuss that. See, if we talk about a paramagnetic material, every atom of a paramagnetic material, every atom of a paramagnetic material, it possesses magnetic moment. Okay, it possesses magnetic moment. Every atom possesses magnetic moment. Okay, and because it possesses magnetic moment, you can see that suppose there is an atom. So this atom, it possesses a magnetic moment in a certain direction. Okay, now what happens that suppose we talk about a material like this, it is a material. Okay, now in the absence of magnetic field, when magnetic field is not present, okay, say I will draw it here. Okay, just a minute. Suppose that we are talking about a magnetic field, when the magnetic field, external magnetic field is 0, external magnetic field apply nahi hui hai. So these atomic magnets, I am calling them atomic magnets because they are behaving as they are acting as a magnet. So they are randomly oriented. They are randomly oriented. Okay, they are everywhere, all over. Now if they are everywhere, then what will be the net magnetic moment of these materials? Net magnetic moment. What will be the net magnetic moment for this material? In the absence of magnetic field, it is 0. No net magnetic moment is there. But what happens that when the external magnetic field is applied, so these materials, okay, what happens, you know that when a magnetic dipole is kept in a magnetic field, like an electric dipole, when it is kept in an electric field at an angle, so it experiences a torque, and because of that it gets aligned with the applied electric field. Similarly, if a magnetic dipole is kept in a magnetic field, that also experiences a torque, and what happens that due to the applied magnetic field, it gets oriented in the direction of the magnetic field like this, gets oriented in the direction of the magnetic field like this. And when it is getting oriented, getting up the torque, okay, definitely now if they are aligned in a direction, see here what they were doing, they had their net magnetic moment, but the problem was there, they had the magnetic moment, but the problem was there, they were cancelling each other's magnetic moment, they were too random. But in this case, now they are aligned in a certain direction, and if they are aligned in a certain direction, what will happen? If they are aligned in a certain direction, then because of that, what happens that the material, it gets net magnetic moment. Okay, so this is what is the reason why the paramagnetic materials, they get magnetized. Okay, because each atom possesses magnetic moment, but initially when B is 0, external field is 0, they are cancelling each other's magnetic moment because they are randomly oriented. But once they are brought in a external magnetic field, then what will happen that they get oriented in a certain direction, and once they get oriented in a certain direction, in the direction of the applied magnetic field, because of that the material acquires net magnetism. Okay, I hope you understand this. Thank you. Magnetic susceptibility of a paramagnetic material, chi m. The magnetic susceptibility of a paramagnetic material is, okay, what is magnetic susceptibility? You all know. Magnetic susceptibility is the ease with which a material gets magnetized. So it is experimentally observed that magnetic susceptibility of a paramagnetic material, it is inversely proportional to the absolute temperature. It is inversely proportional to the temperature. Okay, where this is absolute temperature. Okay, it is defined in Kelvin. Magnetic susceptibility is directly proportional to 1 upon T, or it is inversely proportional to the absolute temperature. Okay, and that's why when you remove the proportionality sign, there comes a constant, and this constant is called Curie constant. Curie, Curie, Curie constant. This constant is called Curie constant. Okay, if you plot a graph between magnetic susceptibility and the temperature, this graph, because they are inversely proportional, so the graph would be rectangular hyperbola. This graph would be rectangular hyperbola, because you know that as you are increasing the temperature, magnetic susceptibility would decrease. But if you are plotting a graph between magnetic susceptibility, okay, and 1 upon temperature, then this graph would be a straight line, because they are directly proportional. Okay, I hope you understood this discussion. Thank you.